All right, so moving on to today. Last time, what we did is we looked at an RC circuit. We spent our entire time analyzing a single circuit, the RC circuit. And we solved for the charge as a function of time and the current as a function of time. And we learned that after doing a lot of math, which made the math majors very happy, and the people who like math very happy, we learned that the time constant of an RC circuit is RC. And here's what we mean by that. Here's our summary. We had only 3 input equations. And then the rest, we simply used logic to derive. Okay? So the 3 input equations were that Q is C delta V across a capacitor. So the charge on the capacitor is its capacitance times its, the voltage across it. And that the voltage drop across a resistor is IR. Okay? And then we also use the fact that in the capacitor, the charge that's gathering on the capacitor is going to depend on the current coming into it, right? And we said that, OK, current I is dq by dt. So here is the answer that we got is that, OK, the charge builds up on the capacitor as we expected, all right? And the current dies out in the circuit as the capacitor gets charged up. It takes the full voltage across it from the battery, and then there's no current flowing in the circuit anymore. Now this current, the one equation that we had to kind of, the phrase that came into my mind was make up. And we did. We made up this equation, OK? I equals dq by dt. We had to figure out that that was the right way to write that. We turned, a physics concept into math, right? And so here was the idea between I equals dq by dt. There's charge gathering up on the capacitor, but we could think of it as like a water hose filling a bucket, right? If you had a water, the current's flowing into the capacitor, dumping charge into it, it's just like water flowing through a water hose and filling up a bucket. And if I wanted to know what's the flow rate through your hose, I could just measure the bucket and watch how the water is filling up in the bucket. And that would tell me the flow rate in the hose. That's this equation. Flow rate of the hose, I, equals the change in the water level per unit time. Okay? Translated into circuit language, that's current equals dq by dt. So we used all those 3 together, solved the differential equation, solved, right? Remember how we solved the differential equation? How do you solve a differential equation in a physics class? Know the answer. Thank you. Okay? You know the answer from the mathematician, and then you make it match your physical situation. And so we saw then that we could get the mathematical form. And all of these curves go like exponentials with an exponential that goes like e to the minus t over rc. And we learned that you can't exponentiate something with units. So this t over rc must be unitless. Therefore, rc must have units of time. So rc is the time constant of it. Do you have any questions about that? This is about discharging. And the question is the following. We have a capacitor that's initially charged. Which of those graphs shows the current versus time while the capacitor is discharging? All right. There must not be much argument going on. Everybody seems to be pretty much in agreement. So I heard the conversation die down, so I'm just assuming that's because you have consensus. So what are your thoughts? Which one did you choose and why? OK. All right. So it's discharging. The current has to eventually go to 0. And so in the long time case here, I must have something that goes all the way to 0, right? So that rules out A and B. This guy goes to 0. How did you choose between C and D? Because C also goes to 0. Right? OK. So you knew that. All right. I'm just going to put the 2 together. You tell me if I'm getting it right from what you said. The long time behavior must be that the current dies out, right? Because we've seen it happen. We take a charged capacitor, hook it up to a light bulb, glows for a little bit, and then dies out. So that must be the case. It's got to be either C or D. And if it starts off initially charged, then it must be that in the interim, right, when I first hook it up, it's kind of like the capacitor gets to pour out its bucket of charge, right? So there must be some current initially. So that's this guy. All right. Any questions about that? So in this case, we're going to say that the capacitor is initially uncharged. Okay? And which of those graphs shows the magnitude of the potential difference across the light bulb filament while the capacitor is charging? So now we're looking for voltage across this guy, the light bulb, versus time. All right, this one's harder. All right, there's actually a good divide between your answers right now. A lot of people are choosing B and a lot of people are choosing D. So we have this B-D divide in the class. Okay? So how are you going to choose between those answers? Okay, all right, so she's answering it by going back. There's a lot of different ways to get to this answer. So she's answering it by thinking first in terms of the capacitor. Okay, she knows that this is a case where we're charging the capacitor. So as we charge up the capacitor gathers charge. And as the capacitor gathers charge, the voltage difference across the capacitor increases. So she looks at this and says, look, B is actually the right answer for the voltage difference across the capacitor. On the other hand, we're asked for the voltage difference across the light bulb. And if I go then with that the battery has a particular constant voltage across it, then the voltage drop across the capacitor is growing, right? Then it must be that what's left to go across the battery is getting smaller and smaller. Is that essentially the line of reasoning? Okay, so she's choosing D based on that. We're going to discuss today Ohm's law, series and parallel resistors, and series and parallel capacitors. And if we have time, we'll get to how you measure things in a circuit. Okay, so ammeters and voltmeters and ohmmeters. Oh my, ohmmeters, okay? There's actually more than this that you can measure inside of a circuit. You can also measure capacitance and inductors, okay? All right, so conventional current and electron current, I just want to remind you what these guys are like. This is directly from lecture 12. So lecture 12, we had electron current, which is the number of electrons per second passing a particular spot in the circuit. And then we saw that to convert that into conventional current, we just needed to multiply by the magnitude of charge on an electron. Okay? And so conventional current is in coulombs per second. This is just to remind you what goes in microscopically to the current equation. That the current is magnitude of Q times N times AV. All right? So the Q here is the charge on an electron. Little n is number of electrons per unit volume. V is the drift velocity. Okay, so you combine all that together and you get the total current in the circuit. So QNAV. So if we look at this, that's going to help us then get what's called a conductivity. So I'm starting here on the left, I equals QNAV, with something you already know, right? You already know that current equation. Now, we also know that the drift current is proportional to the electric field you apply, right? So think of yourself inside of a material, an electric field gets applied, there's a particular drift current that happens to the electrons, and we know the microscopics of that, right? Each electron gets accelerated by the electric field, right? But even though they get accelerated, they're smacking into things and losing their kinetic energy periodically. And so each electron has this strange kind of start-stop, 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 start-stop motion. But if I average over time, there's a net drift velocity to these electrons, and that's this guy. And so the drift velocity is the mobility mu times the electric field. Mobility mu is just a number that is associated with a particular material. So you tell me it's copper, or you tell me it's nichrome, or you tell me it's some other material, and there's a mobility associated with that. For a given electric field, there's a particular drift velocity that comes out. So now then, the current I can think of as combining all these guys together, and then I'm going to put in that the drift velocity is the mobility times the electric field. But what I'd like to think in terms of is something that's a little bit more intrinsic to the material itself. For this equation here, it depends on geometry, right? The total current that goes through something depends on the shape of it that it's got, right? So if I want to get something that's a little bit more microscopic, here's what I would do. I would say, okay, well, let's not talk in terms of total current. Let's define a new quantity called J, which is current density. And that's going to be the total current divided by the area. I just take out what's geometry dependent. All right? And what's left then is Q and UE. Now I'm left with things that are a little bit more, how do I say this, universal. For a given electric field, right, then I just multiply by the mobility times the density of electrons in that material times the charge on an electron. All of this stuff is just intrinsic to the material. All right. I'm going to make another definition, which is that current density is defined as sigma E. I'm just going to say whatever's in front here, I'm going to call a new quantity, sigma, all right, which is the conductivity. And then I have that this conductivity, Q and U, is also just if you give me a particular material, I can tell you the conductivity of the material, right? Because I know the charge on the electron is going to be the same in every material. The density of electrons, right, number of electrons per unit volume, depends on the material, right? You have to tell me the material, and then I can tell you what that is. The mobility is the same way. The mobility is different in different materials, but it's the same for every hunk of copper. So the conductivity is something that is the conductivity in copper, the conductivity in nichrome, or whatever it is. So that's why we like this J equals sigma E definition. Now, another advantage to that kind of definition is that it gives you good physical intuition about what happens in a case even if you had two carriers. How is that possible? Okay, actually, it happens a lot in semiconductors, which is not something we're going to discuss in this class. But here's a simpler case where you can get two kinds of carriers carrying current at the same time. Let me just put a voltage across salt water. Okay, when I put a voltage across salt water, the sodium ions and the chlorine atoms, ions, want to run in different directions, right? So they dissociate in the water. I have a negative charge on the chlorines. I have a positive charge on the sodiums. And based on the potential difference, they go in particular directions. Think about the sodium guy first, okay? Sodium in water is positively charged, okay? So it goes towards the negative terminal, right? Which way does the conventional current go if I'm just tracking the sodium guys? Which way is conventional current going up here? This way or this way? Okay? And I'm seeing a lot of people go this way, right? Because it's positive. So conventional current tracks the positive charges. What about for the chlorine, right? The chlorine's negatively charged. The chlorine's going the opposite direction. Which way does the conventional current go for the chlorine? I see everybody going, yeah. Okay, it still goes that direction because the conventional current goes in the opposite direction from negative charges. So the conventional current is actually this solid blue arrow up there represents that. So that means that rather than thinking about these conductivities somehow subtracting from each other, they add, right? So whatever the conductivity is of the sodium atoms, ions I should say, the sodium ions, I can directly add it to the conductivity of the chlorine ions. Okay? So I can just add these guys together to get the total conductivity of salt water. And I would simply say, well, what's the charge on the sodium atom times the density of sodium ions times their mobility, and then add it to the charge on the chlorine times the density of chlorine times the mobility of the chlorine. Do you have any questions about that? Okay? All right. Now, resistance, we can define resistance based on this conductivity. It must be that this conductivity has to be related in some sense to the resistance. So how can we see that? We have this J equals sigma E, or another way to think of it was back with the current equals something times the electric field. If I have a particular then hunk of material, all right, it's got a particular L, it's got a particular cross-sectional area, and I'm going to run a particular current through it. I say that the current is, as we derived, Q N A U times electric field. There's this very familiar looking equation, though, which is that the voltage drop across this guy needs to be IR, right? If I have something that follows Ohm's law. So how can I connect these guys up? I can connect these guys up, first of all, if I solve for I, right? But I'd like to also just make a connection between these guys. So how can I connect the electric field in here with the voltage drop across this thing? If there's a total delta V voltage drop, how is it going to be related to that electric field? So our resistance then, this guy was sigma E, all right? So the resistance is then going to be equal to, right, the L over sigma A when you connect all those ideas together. All right? V equals IR is probably the thing that you're most familiar with here, right? And we should really think in terms of potential drop across this guy. The potential drop is I times R. Now, I want to think, though, how do I build this guy up in terms of when I have a complicated circuit and I want to put these guys together, right? So I want to add the resistors together, or I want to add, we'll even get onto capacitors. So let me think about how to put these guys together in series. So I want to add up a bunch of resistors, and I want to think about what's the net effective resistance in this case. All right, a circuit like that, I like to organize it so that I can clearly see where the voltage is going up and where the voltage is going down. Okay, so for the same topology of the circuit, I'm going to write it just a little bit different here, okay, to give myself a little bit better of a visual handle on where's the voltage going up and where's the voltage coming down. So I have over here the battery difference, all right, and then over here I've got the 3 resistors coming down, R1, R2, and R3. So I've got this so that I can quickly visually see stuff on the left is where the potential goes up. Stuff on the right is where potential goes down. All right? And then again, in our analogy about heights and water, that sort of thing, I can think about the battery itself as like a little escalator that's sending the charge up in height. And then each of these is where it's coming back down in height, okay, on the right-hand side. And then your voltage loop law, which is written up here, I find a little bit more intuitive if I've drawn the circuit out this way, so that things that are increasing are on the left, things that are decreasing are on the right. Then you can just see there's kind of like an equal sign already smack in the middle in your circuit, right? Whatever the height goes up on the left-hand side has to equal the height that comes down on the right-hand side. So then we get that the battery voltage must be equal to all these potential drops, right? So I'll have a delta V1 plus a delta V2 plus a delta V3, all right? And as we saw before, we have that delta V is IR, right? Now, tell me about current over here. Current's coming out of the battery, right? And coming into the resistors. So I know there's a particular current coming into resistor 1, right? I. So what's the current going into resistor 2? Same, different? It's got to be the same, right? So your current node law tells you that what comes in has to go out, right? If it comes in, it has to go out. So in this case, everything's just got the same current, all right? So all these voltage drops then, I could say delta V1 and delta V2 and delta V3, all right? These guys are all going to be same current times all those resistors together, R1 plus R2 plus R3. And then if I wanted to say, well, what's the equivalent resistance of all those guys together? If I just draw a big box around them and say, look, those have some effective total resistance in them, it's got to be this guy. Okay? So the total effective resistance is just to add these guys together. All right. Do you have any questions about that? All right, now we could have also seen that. So you get that from, we use 2 principles, right? We use the voltage loop law, right? We also use the fact the current node law, which is that what goes in must come out. So we knew that the current going through all those was the same. That's one of the telltales that you have things in series. If things are in series, then they've all got the same current going through them, constant current. You can see this out of the resistance for a particular material, the resistance being L over sigma A, right? Now, if I have the same material and the same cross-sectional area for all these guys, so let me just say that all 3 of these are equivalent, then the only thing that's going to be different for the effective resistance, right, is the length. It's like just taking, if I had, if these guys represent these resistors, if I'm putting them one right next to the other and they're all the same, I may as well think of it as one big resistor. It's just 3 times as long, right? So, what I get from here is that a longer hunk of material has a higher resistance to it. Okay? So this, I hope, is very intuitive, that the effective resistance of things in series, you just add them together, because you're just essentially going to add up the lengths, right? So add up length, length, length. Do you have any questions about that one? All right. When things are in parallel, it's a little bit less intuitive, but we'll see that it comes out of the equation for resistance as well. So in this case, we have the battery here on the left. We have 3 resistors now coming down in parallel. If I want to do the same kind of, you should draw your circuits however you like, but for me, I like to put the battery on the left and put the other elements on the right so I can clearly see where the voltage drops are. So using that same kind of idea for that circuit here, I'd have the battery on the left, okay, and then to have things coming out in parallel, well, I just need to make sure that they actually literally are in parallel on my diagram here. And then I can see that the voltage drop across these guys is exactly the same. All right? So I have the R1, the R2, and the R3. And when things are in parallel, okay, delta V is the same. Right? In our series case, right, series had that I was the same. But parallel has that the voltage drop is the same. Okay? All right. And so in this case then, we're going to have that the current comes into this upper node here and splits 3 different ways. Okay, I have the current coming down here, the current coming down there, and the current coming down there. And what I can think about then is, all right, I have the battery voltage here, and then I don't know right off the bat what these different currents are, but we can figure it out, right? So if we know that the current coming in to here has to split through all those 3 paths, we also know that this voltage drop across these guys is the same, right? So I know that if I look at any of the particular loops, right, the voltage of the battery must then be equal to this voltage drop across this guy, the I1, R1. And that has to be equal as well to the I2, R2, and the I3, R3. Sorry, it's an equal sign. Sorry about that. Okay. So then I know that for any particular one of these currents, I can just solve for it. So let me just solve for this guy. And I'll get voltage of the battery divided by R1. Or if I want to use the EMF language, it's EMF over R1. All right. Now, and of course, that would have worked for any of these guys, right? I could solve for I2, and it would also be EMF over R2. And I could solve for I3, and it would also be EMF over R3. So now, taking what we know for the current node law, what comes in must come out, right? Total current I comes into these guys, and I1 plus I2 plus I3 comes out. Having solved this part, right, and knowing that when things are in parallel, the voltage drop is the same across all those elements that are in parallel, I can put the current in, right? So the current, I1, is EMF over R1. That's going right here. The current 2 is EMF over R2. That's going right here. And the current 3 is EMF over R3. Okay? But the EMF, of course, was the same across the entire circuit. That's what parallel means. So I pull that out, and I have 1 over R1 plus 1 over R2 plus 1 over R3. This whole big thing, we're calling 1 over the equivalent resistance, because we're thinking about, all right, I want to think of an equivalent circuit where I have a battery, and I think of this as some black box, and I don't know what it is, but it's some effective resistance, R effective, all right? And then in the case of my black circuit here, right, I would have that the total current also goes through the effective resistance, and then the voltage drop across the battery has to equal I times R effective. All right? So now comparing these guys, the total current is EMF divided by R effective. So all of that together then, cancel the EMFs, and you get that 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3. All right? Now, you could have guessed that from the microscopic definitions here of the resistance. All right? So if I think, well, let's think intuitively first, and then we'll go back to that microscopic definition. So let me use the height analogy and think about water coming into pipes, only I have 3 pipes in parallel. Okay? So if I think about, well, water's coming into one pipe, there's a particular resistance associated with that. If I add another pipe, is it easier or harder for the water to flow? Yeah, it's easier. And if I add a third pipe, it's easier, and so forth. Okay? And that's what we're going to get here as well, all right? That as we're doing this, it should be that the resistance basically is going down because we're adding extra things, all right? So here in this case, I can think in terms of 1 over A. 1 over r, sorry, so 1 over the r. The area, if the area goes up, right, then the resistance should be going down, right? So if I have a wire that's got a particular cross-sectional area, a larger cross-sectional area can transport more current, and it actually, it's easier for it to do it. So larger area means it's got a lower resistance. Same thing here with, if I think in terms of the water pipes, right? 1 water pipe, 2 water pipes, 3 water pipes. There's just more cross-sectional area there. It's easier to flow water through. There's less resistance through this set of 3 pipes. And in fact, I could use this analogy to think that, well, in this case here, when I'm trying to get the effective resistance, the effective area is the cross-sectional area of all 3 together. Okay? Now if I think of the cross-sectional area of all 3 together, I just add them up directly. A1 plus A2 plus A3. And if I'm going to be adding areas, I have to be adding 1 over r's. That's the microscopic explanation of that. But the thing that you need to know, okay, so I hope it makes sense if you think about it intuitively from that sense, but the thing that you need to know in order to solve circuits is that 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3. Do you have any questions about that? Okay. All right. Capacitors. You can do the same kind of circuit reductions with capacitors, of course. So if I take capacitors in parallel, I can think about the equivalent capacitance of these guys together. It turns out the capacitors in parallel add. Okay? But you can kind of see that, actually you can see that, from the capacitor equation that we have for parallel plate capacitors, that the capacitance is epsilon naught A over S. All right? So let me just think intuitively about what happens when I have these 3 capacitors together in parallel like that. Think of this one as having a particular cross-sectional area. This one has a particular cross-sectional area, and this one has a particular cross-sectional area. All other things being equivalent, when I put these 3 together, they can hold a lot more charge, right? So there's just more space for them. And they have a combined area that's larger, right, than before. So if I think about the fact that in this configuration, the areas add, okay, well, capacitance is directly proportional to area. Larger surface area of your capacitor means more place to store charge. Capacitance is about the capacity to hold charge, so this guy goes up. And so if I would add the areas together, in this case, I would add the capacitances together. So parallel capacitors add. Do you have any questions about that one? Okay. All right. Now, series capacitors are going to look a little bit different. We can also get that again from the equation for the capacitance. So let me think about these guys that are in series. Let's see here. If we think in terms of the capacitances being proportional to 1 over S. So this S, remember, is the distance between the 2 plates in the capacitor. All right? So if I'm thinking about 3 capacitances in series, I can think of this as like, well, let me just think of 3 equivalent ones, because it's a little easier to think of equivalent ones. So everything's equivalent. They've got the same gap. This is like distributing, right? I'm going to distribute a particular voltage drop across that, equally across those 3 capacitors, right? Or I could also think about, well, it's like having an effective gap that's 3 times that, right? It's like having 3 S in there. So the S's add, right? It's like the total S is S1 plus S2 plus S3. Well, if I look in this equation here and solve for S, I would be getting epsilon naught A over C. So here, epsilon naught A, I'm saying that A is constant in this example. I would take 1 over C1 plus 1 over C2 plus 1 over C. That's a C3, okay? Which would give me the effective capacitance, 1 over C effective. So you can also kind of see this relation as well coming out of the equation that you have for what's the capacitance under a particular geometry. But the take-home message for you, the thing that you need to be aware of is that 1 over the effective capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. Do you have any questions about that so far? Okay. All right. The summary then is this. all right, for resistors and capacitors in series and in parallel. Okay, and remember, series was if everything has the same current going through it. Parallel is if two things have are at the same spot in the circuit such that their voltage drop is the same across them. Resistors in series add, okay? Resistors in parallel follow this funny law of 1 over R effective is 1 over R1 plus 1 over R2. Capacitors are just flipped from that, okay? So what you can do is think, whichever one of these equations makes the most sense to you. This one right here, for me, makes the most sense, that the effective resistance adds when I have two resistors in series like that. And then the capacitors are just the opposite situation, right? So capacitors in parallel add, whereas resistors in series add. Capacitors in series have that 1 over, I guess you could call it like an inverse addition or something. But anyway, here's your summary slide for that. Do you have any questions about how those reductions go? I have two different circuits, all right? So I have this RC circuit, which has a particular capacitor and a particular resistor in it. Assume they have the same batteries. Assume C is the same in both cases and R is the same in both cases. It's just in circuit number 2, I'm going to have 2 of that same capacitor in series, 2 of that same resistor in series. And what I want to know is which of these circuits has the larger time constant. All right? So you got to do the circuit reductions over here to get that time constant. OK, what are you thinking? Which one should we think about? Yeah? OK, so you got that they're the same. Let's see. I'm going to put that guy up. All right, I'm just going to write out what you're seeing. OK, so the one we have to reduce is this guy on the right, right? And then we've got the 2 capacitances and the 2 resistors, right? You're saying the effective resistance is just that they add R plus R, 2R. And then these guys, you have to use the series law for the capacitors. So you add 1 over the C's. It's 2 over C, right? So then altogether, this guy's equivalent to, well, its time constant is going to be its R effective times its C effective. You got the 2R times the C over 2. The 2's cancel, and I get that they're the same. OK? Yeah, awesome. And we're going to be done with class for today.